W students, my 3 W's, I need you to stay afterwards because we have to talk about the next assignment. So don't let them go, and then I'll try to end it early. Okay, so chapter 18. Electron transport and oxidative phosphorylation. Everything that we've done, starting with glycolysis, has been to oxidize glucose in order to make ATP. So if we go back, again, our overall reaction is our glucose, and then we have our oxygen, and we're going to make carbon dioxide, and we're going to make water. And if we break this up into half reactions, the oxidation half reaction is the glucose going to carbon dioxide. And from that, we get some protons, and we get some electrons. And then the reduction is where our oxygen's going to pick up those protons and those electrons. And we end up with water. So the first half reaction is done. Okay, so that's glycolysis in the CAC. We've turned our glucose into carbon dioxide. We've done that. Okay. The second half reaction is yet to come. And that is our electron transport and oxidative phosphorylation. Okay. So a while back I made you balance that redox reaction and then tell me that it's 24 electrons that get passed between the two half reactions. And so now we can actually look at to where that comes from. So for glycolysis in the citric acid cycle, how many NADH total did I make? 10 for 1 glucose. And how many ADH2s did I make for 1 glucose? 2. When NAD is reduced to NADH, how many electrons does that take? 2, yeah. So there are 20 electrons here being carried by NAD. And then FADH2 is the same thing as 2 per molecule, so that's 4 electrons. So there are my 24 electrons. They're all tucked into these electron carriers right now. There it is. Back up there, 24 electrons. And so my final destination electrons is what? Oxygen.
Oxygen, yeah.
To reduce it to water. Okay, but my electrons are going to go right to oxygen. You have to go through the electron transport tube first. Compartmentalization. That's a long word. We talked about this a little bit already. Okay, glycolysis happens where? In the cytosol. Okay. CAC occurs where? Mitochondria. Now we have to be more specific.
Matrix.
Matrix. Okay. Some of the enzymes are attached to the interface of that inner membrane, but not all of them are. So this is mitochondrial matrix, and it's on the matrix side of the membrane. Electron transport. Where's that one happen? Inner membrane. This is kind of across, well, I think I would just say in the mitochondrial inner membrane. And then when we get to the proton transport, that's going to be across the membrane. Alright, so we got our picture of a mitochondria. So two membranes. There's an outer membrane and an inner membrane. So cytosol out here, in between the two membranes is the intermembrane space, and then inside the inner membrane is the matrix mitochondria. And the little, how do we say that? Christe, how do we say that?
I think.
All the invaginations, right? This is just to give a lot of surface area, because we need a whole bunch of electron transport complexes in that membrane. So the more surface area you have, the more complexes you have, the more ATP you're going to be able to make for the end. So your outer membrane, we talked about mitochondria permeability. The outer membrane is very permeable. I'm going to say to most anything. Yeah, at some point you get like really big proteins and you can't pass but it's permeable to most anything less than 10 kilodaltons the size. So this is effectively the same as the cytosol. And we're not really going to make a distinction between the two. We're just going to call the intramembrane space to be the same as the cytosol. Okay. Intermembrane is different. I should probably put another word in here. That your intermembrane space is effectively the same as the cytosol. The inner membrane is only permeable to some small molecules. assuming they're usually neutral. Okay, and the ones to know are oxygen can pass carbon dioxide and water. All other species must be transported. By some kind of system, and that system is going to vary. Okay, so we're going to talk about a few of these transport systems. We need one for NADH, and you actually know what that is.
Is that the oxo? Yes. Okay.
There's a shuttle. Yeah. So my malate aspartate shuttle, and remember this is for transport of oxaloacetate out of the matrix and into the cytosol. Can be used to transport NADH. So when oxaloacetate is turned into malate, that is a redox reaction. And it's a redox reaction that involves NAD. So when we talked about it before, it was because we wanted to show that we could pull oxaloacetate out of the citric acid cycle to feed into gluconeogenesis. So we're trying to get it from the matrix side to the cytosolic side of that membrane. And you can do that one of two ways. You can either turn it to aspartate, and then there's a transporter for aspartate, or you can turn it into malate, and then there's a transporter for malate. Oxaloacetate, the NAD gets oxidized, which means the oxaloacetate gets reduced. So this is a reduced form in that process, and then the reverse reaction to turn it back into oxaloacetate takes the NAD and reuses it again. That's great for taking oxaloacetate out of the mitochondrial matrix and putting it over here. But if this thing operates in reverse, then I can basically take an NADH, which would be coming from what process, what metabolic process is in the cytosol in this NADH? Glycolysis, yeah. So NADH is made in glycolysis. And it oxidizes it here, but then the oxidized form on this end ends up getting reduced. And so I just go backwards, then I can transport NADH, not physically, but the reducing equivalents across that membrane. And then this can work in a little cycle, because then I can turn oxaloacetate into aspartic acid, and move it over, turn it back into oxaloacetate, and I can go in a circle which constantly moves those reducing equivalents over into the matrix without any net change in the amount of oxaloacetate I have on either side. So this is kind of a convenient system for moving NADH. Transport of cytosolic NADH into the mitochondrial matrix is coupled to transport of oxaloacetate into the matrix. Does that make sense in terms of metabolic need? am wanting to move NADH into the matrix, it's because I want to synthesize what? ATP. Why would I want to move oxaloacetate into the matrix?
The citric acid cycle.
So citric acid cycle intermediate, what does happen to the citric acid cycle if I increase one of its intermediates?
It all increases.
It all increases, yeah, all increases. And so you upregulate the CAC, which is also something you want to do if you are desperate for ATP. You want to upregulate that. So yeah, I think that makes sense. Although you don't have to do it that way. You can use the cycle and then have no net change. Just open net NADH into the matrix. Oh, oops, I'll show you this one too. If you're an insect, I don't think there are any of those in here, but if you're an insect, there's another method for transport of NADH electrons into the electron transport chain that doesn't involve that shuttle. And basically, you end up transferring the electrons from NADH to an FAD. And this is the same FAD that you're going to see basically in the citric acid cycle that is the prosthetic group of the 6 and 8 halogenase. And it's just via this phosphoglycerol dihydroxyacetone cycle. So we end up reducing the dihydroxyacetone phosphate to make the glycerol, and then it passes its electrons and becomes reoxidized to that when FAD gets reduced. And so it actually never crosses officially into the matrix. It gets moved directly to that membrane and right into the electron transport chain. But that's only if you're an insect. So NADH, you can use the malate aspartate shuttle. Can be used to transfer NADH into the matrix. From the cytosol. And remember, this is a product of glycolysis. And then if you're interested in insects, you can use the glycerophosphate shuttle. And that's where electrons from NADH are passed to FAD in the inner membrane. Great, so now all of our NADH, out of our 10, are now inside the matrix. Yeah.
Does that mean that because FAD doesn't create as much ATP in the electron transport chain that
Yes.
are less efficient?
Yes. We're going to talk about that. Yeah. It has to do with how many complexes in the electron transport chain you travel through.
Okay.
Okay, so next thing we need, if we want to make ATP, then we're going to make that from ADP. And so you need a system for bringing ADP into the matrix and for exporting the ATP that you're synthesizing. And this is transported via an ADP-ATP translocator. And this results in exchange of ADP, let's say net exchange of ADP from the cytosol for ATP to me version. So my translocator is in yellow, and this is, outside to inside. I'm not quite sure why they drew some things, but they're showing that I can have ATP or ADP bind here, and it's going to transfer to the other side. I can have ATP or ADP down there, and it can transfer to the other side. And in the end, ADP is going to come in, and ATP is going to go out. Is that an example of an antiport? So that actually is crazy talk. In an antiport, you have something on one side, something on the other, and they both have to bind, and they both get moved in the opposite direction. In this case, in the end, it's kind of the similar effect of an antiport, but what's happening is it's just an equilibrium. So I can have either one bind to one side and be released to the other. And it's just one thing at a time, right? Which means something has to drive this transport. So what's going to drive that transport? This is going back to chapter 10 from last semester. What drives transport across membranes? Okay, so transport is driven by a concentration gradient. So that would be a chemical potential, right? For transport. And there's another part to that equation. Yes. So by membrane potential. So this is an electrical potential. You only see that if the species being transported is charged. Is ATP charged?
No. Yes.
Yeah. Phosphates. I got phosphates. The negative charges
Oh
on
yeah,
phosphates.
super.
And ADP too, but the charge is actually different. So ADP has a -3 charge, and ATP has a -4 charge. Do you believe me?
Yeah.
Yep. If I have, let's just do it this way for the rest of the ATP, but if I have this, with just 2 phosphate groups on it, 1, 2, 3. And if I have 4 phosphate groups, or 3, I don't know what it is, tetraphosphate. 1, 2, 3, 4. The inner membrane space is highly positively charged. Because of a proton gradient. And we haven't come to how that proton gradient was established, or we're going to come to that in a moment. But that inner membrane space is very positively charged, which means that in order to try to eliminate the potential or to have a net free energy change of 0 at equilibrium, I'm going to pull the more negative thing out of the matrix and put the less negative thing into the matrix to try to diffuse that electric potential. And this is really the major store that one. That is the major reason for the transport. Okay, but yeah, that's going to get our ADP into the matrix, so we can turn it into ATP, and then we'll ship it right back out again. Okay, to make ATP, you need ADP, but you also need phosphate. So this is transported into the matrix by a carrier protein. Symport. So what do symports do?
Doing two things at once.
Two things at once, two things together. And what do I have a lot of in my intermembrane space that we just mentioned?
Protons?
Protons, yeah. So it transports inorganophosphate with a proton, and it's going to be again, it's going to be both a concentration gradient and a potential, electrical potential gradient that drives it. And that way we can bring the phosphate in. So that's pretty much what we need, right? Oxygen and water is just going to diffuse across, so we don't have to worry about that. We got our ADP brought in, ATP can leave. We've got our phosphate we can bring in. Now what we need to talk about is how to make the proton gradient. So electron transport. This is a series of proteins and prosthetic groups, and those might be cofactors or coenzymes. That vary electrons from NADH or FADH2 to oxygen, which is our final acceptor of the electrons. It does this by using differences in reduction potentials. To drive transport. And this occurs in the inner membrane of the mitochondria. If we look at the reduction potentials, if we look at NAD, maybe NADH, and I look at a reduction potential here. And for these are reduction potentials, not changes in. A few people have some trouble with the labeling on the exam where they wanted to put deltas in front of these, but we haven't taken the difference yet, so there's no delta in front of that. For NADH is a negative 0.315 volts. And then if we look at reaction for oxygen. Being reduced to water. That reduction potential is a positive 0.815 volts. What have we said about electron flow? Which way does it want to go?
Lowest to greatest.
Smallest to greatest, yeah. So always going to move towards the bigger reduction potential. So electrons want to move from NADH to oxygen. They want to go in that direction. And we can prove it, okay? So if we couple these together, so O2 has higher affinity for electrons. That's the greater reduction potential. And if coupled, where I have the whole thing, so 1/2 of O2 plus an NADH plus OH plus going to water plus NAD. And then my change in reduction potential, and I'm sorry, these are standards, I should write that up there. My change in the standard reduction potential is going to be that difference between the half reactions, where you can flip the one that is oxidation and then add them, and that's fine. So this is going to be 0.815 volts minus a negative 0.315 volts. And that should be equal to 1.130 volts. And now what's my equation for free energy? Equals N. Okay, so I'm just going to plug that in. So what would N be in this case? 2. Oh, there's a negative sign in front of that, isn't there?
Yeah.
Yeah. 2. And F is 96,485 joules coulomb, or joules per mole. And then my E was the 1.130 volts. And so my standard free energy change here is a whopping negative 218 kilojoules per mole. That's how much free energy I'm going to get if I move those electrons, those two measly electrons from one NADH to oxygen. All right. How much energy does it take to synthesize ATP from ADP? Yeah, so 30.5? So 30.5? Yep. So if I take ADP and I add inorganic phosphate to it to make ATP and water, and you look that up on your chart, that free energy change, standard free energy change is a positive 3.5 kilojoules per mole. How many ATP did I say you could make from one NADH? 2.5. So if I take 2.5 times 30.5 kilojoules per mole, what do I get? 76.25. This is energy needed to synthesize 2.5 ATPs. And how much energy did I get from one ATP? Did I say it backwards? From one NADH. How much? Transferring 2 electrons from NADH to oxygen, how much energy did I get?
218.
218. So, is there enough energy to synthesize 2.5 ATP?
Yeah.
Yeah, is there enough energy to synthesize more than 2.5 ATP?
Yeah.
Yeah, so why don't I make more ATP?
Because you don't have any more.
Oh, yeah, we're lousy. So our efficiency, although, you know, we're so much better than anything man-made. But the efficiency here is, I think, 76.25 kilojoules per mole divided by the 218 kilojoules per mole. Is about 35%. This is under standard state. Okay. Are we at standard state in the cell?
Mm-mm.
No. Okay, so under physiological conditions, efficiency is closer to 70%, but it's still not 100% efficient. Why wouldn't it be? Because of, we have to keep our body warm? Oh, yeah, we have to keep our body warm, yeah. So heat is, that's always a good thing. Typically in any sort of energy transfer process, you always lose something in heat transfers. You lose things in just molecular vibrations. So that's probably the biggest reason is heat loss. There are processes in your body that uncouple proton transport from ATP synthesis. There are dangerous dietary aids out there that will do the same thing, but you can generate heat in your body by uncoupling that process. So that's probably the biggest one. There are always going to be other processes that pull things away, and usually it's going to be biosynthetic. Yeah.
Wouldn't that inorganic phosphate transport back in be kind of making it less efficient for ATP synthesis?
Yeah, no, so the transport process for the protons, absolutely. So that's going to decrease your proton gradient, and yeah. So, heat loss, but other transport processes. That diffuse the proton gradient. That 70% is still really, really good. When you start thinking about, you know, like your car and how much energy can be released from all the fuel that you burn versus how much of that is actually translated into the engine of your car. So the electron transport chain. So electrons are going to flow from high to low reduction potentials. Or from low to high, excuse me. So I'm just going to make a little chart. This is full of electrons, starting with NADH. NADH is going to pass its electrons to complex 1, which then is going to pass its electrons to coenzyme Q, also known as ubiquinone. And that passes its electrons to complex 3, which passes its electrons to cytochrome C, which passes its electrons to complex 4, that finally passes the electrons to oxygen. How do I get it on the screen? There we go. Here's the difference between NADH and FADH2. FADH2 passes its electrons to complex 2. That then passes its electrons to coenzyme Q. And then after that it's the same. Each complex contains multiple redox centers. And remember, these are proteins and these are coenzymes and cofactors. We've got metal clusters in here, and they're all redox centers. So this includes coenzymes and metal clusters. Complex 1, 3, and 4 all couple electron transport to movement of protons from the matrix to the intermembrane space. And that is against chemical and electrical potentials. It's against a gradient. Since FADH2 skips complex 1, it doesn't make as much ATP. So NADH is approximately 2.5 ATP, and FADH2 is approximately 1.5 ATP. So, since we don't get those extra protons transferred across the membrane, at complex 1, when it's FADH2, in the end, it doesn't make as big a proton gradient, and we cannot synthesize as much ATP using that gradient. So that's where the difference comes in. So we basically just drew this chart. So there's my NADH, complex 1, there's my FADH2, which again is a prosthetic group of mycelic dehydrogenase that is embedded in the membrane. So it's already in the membrane and it just passes everything to complex 2. And then they meet up at coenzyme Q, complex 3, cytochrome C, complex 4, and then on to oxygen. And this scale here then represents reduction potentials for the complexes. And the actual potentials vary a little bit, but in general, you're always going from a low reduction potential to a higher and higher and higher reduction potential. And that one is on this chart.
Oh.
So here's my NADH. You don't memorize this. At the minus 3.315 volts, and then here's my oxygen at the positive 0.815 volts. And so we're trying to go from there to there. And there's some places where it goes backwards for the standard potentials, and again, that's standard state conditions. But in general, we're always going from the lower to higher potential. So it's going to pull electrons in that direction. And then this actually does break down what all the different redox centers are. And we're not going to talk about these in a lot of detail, but you should know that there are a lot of flavin molecules that can accept electrons. There are a lot of these iron sulfur centers that can accept electrons. So we're just going to pass them along. There's a heme that can take electrons. And there's some copper there at the end that can also act as redox centers. So they're just all molecules that can accept and donate electrons. And then we get to the coenzyme Q and the Q cycle. And I'm sorry, this is probably going to be on Friday, so you might not want to miss Friday if you can help it. It's a bunch of single electron transfers, and it's really confusing. So I'll just warn you up front, but it's not an easy pathway. Which we're going to do Friday. That's my pitch for come Friday. Please don't skip my class.
Come Friday, it's very complicated.
All right. And we're going to stop there because I need to talk to my writing students.